We are one of the teams from RBC taking part in TI ADC competition. Our problem statement corresponds to team C. This is our setup. This is the analog starter kit from TI, and our CRO, DC power supply, and a signal generator. So now we'll look into the theory behind our problem statement. This is a Tau Thomas biquad filter. It's biquad because the numerator and denominator of this transfer function is quadratic, which makes it a second order filter. And this is our design, and it can be operated as a band pass filter or a low pass filter. Since we're taking the output from this point and feeding input here, it functions as a low pass filter. This is basically a band pass filter, and this is an integrator which operates as a low pass filter. Our values of R and C are taken such that RC comes up to 1 millisecond, and on substituting the values of our RC into the transfer function calculated, the transfer function boils down to this. The pole location of our transfer function is at 500 radians per second, and the corresponding Bode plot looks like this. There is a minus 40 dB per decade fall after 500 radians per second. So as you can see, we're at very low frequencies, around 70 hertz. Our input wave, which is the yellow one, and then our input wave, which is the blue one, and then the output wave, which is the yellow one, both of them are like the output is not attenuated at all. So on increasing the frequency to around 80 hertz, which corresponds to 500 radians per second, we get a 180 degree phase shift between the output wave and the input wave, which corresponds to two poles being at the same location at 500 radians per second. So now we continue to increase our frequency. As you can see, the output wave dies down at higher frequencies. So hence our filter acts as a low pass filter. The second part of our problem statement is making our filter voltage controlled. Basically we do that by adding a mixer at the output of the band pass filter, that is the input of your low pass filter, and the mixer mixes the input of the low pass filter with a DC value of 1 volt, 5 volt and 8 volt, and we take the corresponding readings for each set. Now we look into the problems we faced and how we overcame these problems. So basically the voltage we mix with our input to the low pass filter is around 1 volt, 5 volt, 8 volt, like I mentioned earlier, which is below the 10 volt DC supply we use. Hence we devised a voltage divider which gives us the voltage we need to mix. And by varying the potentiometer, which is of 10K, and we can change the voltage we get at the division. Okay. And to find the phase difference between the output wave and the input wave, what we did was we used the cursor of the CRO to find the time offset between the zero crossing of the input wave and the output wave. But we just get the time offset. We need to find what fraction of the total time period is the phase difference. So for that we wrote a script. We scripted it in MATLAB. This is basically our program, PD main and PD. PD main calls the function which determines the phase difference, This gives a fraction of your main period. So let me run it just to show you how it works. So let's say the time period of the original wave was 5, and then the times offset was 5 by 4. So the phase difference, the fraction of your time period is 1 by 4. So the output should be 0.25, and that's what you get. So this is what we use to find the phase difference. Thank you. This is the end of our demonstration.